Hello, hi everyone, welcome back to the channel. So this is Ramandeep Singh, and I hope you are doing really well. I was busy for the last few months, so I could not upload any video over my YouTube channel. But from now, I will try to upload videos regularly, and I'm planning to build a repository for all the CSES problems that we have, and I'll be solving the problems, and I'll also upload it over a dedicated website for CSES specifically. So CSES, let me tell you what a CSES is. CSES is a basically a website where we have problems, data structures and algorithm problems for various topics, starting from very introductory lessons, introductory problems, mathematics, arrays, strings, segment trees. We have advanced mathematical techniques as well. We have string algorithm problems. We have tree problems. We have graph problems. We have DP problems. So if someone is a beginner and starting to look for a complete, an A to Z resource where the person can start from a very basic and can move up to very advanced topics, which are not like usually required even in interviews or in coding contests. Yeah, you may face some advanced techniques in some coding contests, but not all. But here in this particular session, in this particular streak, the CSES streak, I'll try to solve every single problem of the CSES as much as I can. If I could not solve, obviously I will discuss it with other people who are like me in my circle, and will provide the solution to you people. And today marks the day when I'm starting the CSES streak, and I am committing this that I will complete this. I'm at least uploading one video every single day, and for the next for this particular entire year, you know and I'll try to cover the entire CSES set. You people stay with me, and let's start this journey. Let's start with this particular the first problem of the graph algorithm session, and yeah, let's begin. So CSES set, and let's solve this. It's an easy problem. The problem is you're given a map of a building, and your task is to count the number of its rooms. The size of the map is n into m squares, and each square is either a floor or a wall. You can walk left, right, up and down through the floor squares, but not through the walls. Of course, you can't pass through the wall. You can walk where there is a floor, but you can't pass through the wall. Okay. The first input line has two integers n and m, the height and width of the map that has been given to you. Then there are n lines of m characters. Then there are n lines of m character, and yeah, the height and width of the map. Then there are n lines of m characters describing the map. Each character is either a this dot, which represents a floor, or a hash, which represents a wall. We have to return one integer, the number of rooms in the particular map. So let's understand this with an example. So let's take an example here. Why it's not a So let's analyze this particular example which has been given to us. So here we have like 5 rows: 1, 2, 3, 4, 5. You can number them: 1, 2, 3, 4, 5. Right? And then we also have some, what do we call them? We call them columns. So 1, 2, then we have 3, then we have 4, then we have 5, then we have 6, then we have 7, then we have 8. So like this we have rows and we have columns. Okay, so first we have this row, then we have this row. Now this dot part is the floor and this hash part is the wall, right? Dot part is the floor and the hash part is the wall. So let's count the number of rooms. We can see that these two dots constitutes a row. So this is room 1. So we have floor and then we have floor. So we have floor surrounded by the walls. Wall, then we have wall, then we have wall, and then we have vertical walls. So room number 1. Similarly, we have room number 2. So this is room number 1 and this is your room number 2. Why this is a room number 2? Because we have walls above it, we have walls below it, we have walls towards left of it, we have walls towards right of it. Similarly, we have a third room which is here. These are the floors. This is floor, this is floor, this is a floor, floor, floor. So these are walls, and these are floors. Okay. This is room number 3. This is room number 3. So how many rooms we have? 3 rooms. So the answer is 3, right? The answer is 3. So I hope you understood the problem statement, what we have to do, and the solution is also very simple. All we need, we just the solution to this problem, just pause the video here and try to think about the solution for this problem. What can be the solution? Just think about it. So if you have if you have studied about performing DFS and BFS in a grid, then this problem is a very introductory problem for that. That is, just perform a depth first search over this particular grid and you will get the number of rooms. So this is the problem is nothing but the number of islands. You must have solved this problem, number of islands. Lead code, right? This problem. So the problem is nothing but this number of islands problem, right? So we'll convert this problem to that. So let's represent this hash with the 0 and this dot with the 1. And let's convert this thing. Let's convert the entire system into that island, number of island problem. So here we will have 0, we will have 0, we will have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then we will have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this is your modified matrix. This is your modified matrix. These are your number of rows and these are columns. So now in this particular matrix or the grid, you just have to count the connected components. So this is a connected component 1, and this is your second connected component, this one, and then this is your third connected component. Why it is a connected component? Just think about it. Because I can move from any cell to another cell without facing any obstacle. Like let's take this third connected component, this one. I can start from here and I can move to any other cell which contains 1, right? I start from here and I can move to any other cell of this particular connected component. Start from here, we can move to any other cell of this particular connected component. But I can't move from this one to this one. Why? Because there is an obstacle. Given that I can only move from a particular cell towards left, right, up and down. If these 4 moves are allowed, if these 4 moves are allowed and we can't visit this particular place 0, why? Because this either contains a wall, so we can't visit a wall, or in number of islands case we can't visit water, we can visit only the cell which contains the land, right? So similarly here it is simple, we start from here and we can move to any other cell of this particular connected component. We can start from here and we can move to any other cell of this connected component. That is your first, that is your second, and that is your third component. So we just have to count these connected components in this particular grid, and we know very well how to do that. To count the connected components, so all we need to do is to just run a depth first search strategy on this grid, and keep calling the DFS function for the cells which contains 1. So for this cell, this contains 1, call DFS. Now the DFS is going to visit all the cells, the adjacent cells which can be reached from this source. So from this one, I start DFS from here, I will visit this, let's mark it green. Then from here, I can't move up, I can't move towards left, I can't move down, but I can move towards right 1 unit. So I'll visit that cell as well. From here, I can't move up, can't move right, can't move down, can't move left, because left we have already visited. So my depth first search ends here because I can't move. So I'll backtrack to the previous node from where I came. Now I have visited all of the 4 directions of this cell as well, up, down, left, right. So that's all. So I'll move back to the calling function. So this entire component has been visited and I'll count it as 1. Now these 2 cells have already been visited, so I'll mark them visited in some separate array to not repeat the depth first search, right? So to avoid the redundant depth first search traversal. Now let's move to the next cell 0. We can't. Now I'll start my next DFS from here as well. Why? Because this contains 1 and this has not been visited yet. This cell has not been visited yet. Start DFS here, visit it, move up, left, down. I can see that we have 1, so move there, visit it, left 0, right 0, down we have 1, and then we visit that cell. Left nothing, up already visited, right we have 1, so visit it. Then here up 0, left 1, right 1, so we visit it. Left 1, right 0, down 0, up 1. Then from here, left right 0 0, down 1, up we have 1. Then left right anything, left we have 1, so visit 1. So in this fashion we will have ones. So we visited all the ones, right? We have visited all the ones and we are done. Now start from here. I can see that I have visited all the ones and I which were reachable from the starting node, and that counts the second connected component in the grid. Now move to next cell here, 0 0 0 0 0 1 visited, 0 1 visited, 0 0 1 unvisited. So start third DFS from here, visit it, move to the adjacent cell, visit that as well, done. Now I started my third DFS from here, so I counted the third DFS, and that gives me my answer. 3 times I started, or I called the DFS function. That means there are 3 connected components, or we can see there are 3 rooms in this particular system of walls and floors, right? And that's just all. Now the prerequisites to solve this problem or to understand the solution well is depth first search on the grid. You people must know how to perform DFS over the grid in order to understand this problem well. And now let's jump to the code implementation part of this problem. So let me start on one test case. I'm going to solve it here. In this solve function I will solve this. So let's take n and m. These are the dimensions. Let's create a vector or grid of zeros and ones, n into vector of. So the grid that we will have will be of dimensions. So this basically gives me a grid of dimensions n into n, right? So here I am having a grid of dimensions n into m, right? Now this grid contains 0, and now I'm going to read the input. So here we will have character C, read the character C, and then grid ij is equals to assign. When the character is a dot, we're going to assign 1 to it, and yeah, that's all. So if we have C is equals to dot means we have a floor, so we're gonna mark the floor separately as 1. Otherwise when we have walls, we will simply say the cell contains 0. We also create another visited array which will be of the same dimensions n cross m, and we can take it as a boolean array, or I've taken it as an integer array. You can take it boolean array, it would be better. It contains false. False means nothing is visited, right? No cell has been visited yet. Now here I'm going to iterate over the grid again, right? Iterate over the grid, and if I find that at any cell, iterate over the columns. So if at any cell the cell contains 1, and the second condition is that 1 is not visited, that cell is not visited, right? Then I'm going to increment my answer by 1, and I'm going to call the DFS for that particular cell. So let's create an answer variable here, and this final answer will be my number of connected components, or the number of rooms that we have in the system. So this function we have to write, that is DFS function. It simply performs the DFS starting from this cell I comma j and traverses that particular component entirely, right? So now let us create that function as well. Void DFS int I j. Now we have n, we have m, we also need the dimensions here, right? N comma m comma visited array. We'll have a visited array which is boolean array. We will also have the grid, and then here visited ij would be true. Then let's move in the 4 directions. So these are direction vectors I'm defining, direction vectors would be like how we are moving along x direction and how we are moving along y direction, like say 0. So if I'm moving -1 towards x direction, means I'm moving in the negative x, that is going to give me this particular pair, dx is -1 and dy is 0. That is going to give me like moving linearly towards negative x. Simple. Now if I have 0 1 as the pair, 0 and 1 as the pair, I am moving 1 unit above the x-axis, or like not above the x-axis, like we can say that we are moving up. So this is for up, 0 in the x direction but +1 in the y direction, that is we are moving up. Here we are moving left in the previous pair, -1 and 0. In the next pair is 1, means I am moving in the positive direction of x, and I am not moving in any direction along y. So that is I am moving right. Then I have covered up, left, right, and now I'll have to move down. Move down means 1 unit in the negative direction on the y axis, or we can say down, 1 unit down. So it's like -1 is, it's like left, so I'm moving like this, left. Then 0 1 means up, then 1 0 means right, then 0 minus 1 means down. So left, up, right, down. So we are moving clockwise, right? So in these, according to these direction vectors, I'm going to move. So I have my starting cell, I have marked it visited, and let's calculate the new directions. So new direction, new, let's call it new row. So new row would be old row plus dx of I. So let's first d is equals to 0, d less than 4, we have to iterate 4 times now. Now the new direction would be, new row would be I plus dxi, new column would be j plus dyj. Now if this ni is greater than equal to 0, nj is greater than equal to 0, ni is less than equal to less than n, and nj is less than m. And also we have to say if visited of ni and nj, it's unvisited, na? And one more condition we have, that is it should contain this new grid ni and nj should contain 1. If it is the case, then I'll move to that cell. So I'll call recursively the same function for the new row and the new column. Nm will be as it is, pass visited, pass grid. Okay. So I hope it is good, and I don't think I have anything left in this DFS. It's going good. Nj less than m, not visited ni nj, and grid ni nj is equals to 1. Yeah, I think it will work. So let's try over this example. And the space complexity will also be n into m, because like we are using recursion, so that is going to, like, in the worst case we may have call stack full filled with the function calls equal to the number of cells that we have in the matrix. And also this space is contributed by the visited array that we are using. So this is your time complexity, this is your space complexity. So auxiliary space is also there, auxiliary space consumption, and call stack space consumption is also there. Both are present. So that's all for this video, and I'll see you in the next one. Till then, bye bye, and take care. See you in the next one. Till then, stay tuned with me, and keep solving problems in this CSES, and stay with me, and we will complete the streak.